the principle of relativity. The principle of relativity says that the laws of physics apply just as well in a uniformly moving reference frame, that is to say, in a reference frame moving at constant velocity, as they do in one at rest. I'm going to come back and talk about exactly what that means in a moment, but first I want to get all the cards on the table. The second postulate, I call it the universal speed of light. Most books call it the constant speed of light, or the constancy of the speed of light. To my ear, that's no good. Constant means to me same today as it was yesterday, unchanging in time. That's not the issue here at all. The universal speed of light says that the speed of a light signal in vacuum is the same regardless of the motion of the source, or of the medium, or of the observer. Light travels at the same speed to wit, we always use the letter c for the speed of light, 3 times 10 to the 8th meters per second. In vacuum, regardless of the motion of the source by contrast, if I say that a pitcher can pitch a ball at 98 miles an hour, if you loaded that pitcher onto a truck that's going down the highway at 45 miles an hour and said pitch from the roof of the truck, then the velocity of the ball relative to ground, of course, would be determined by the velocity of the source, the velocity of the pitcher. You can make the pitch go a little bit more than 98 miles an hour by running forward while you're pitching it. So a pitched ball has a velocity, given velocity, relative to the source. But light is not that way. It's irrelevant what the motion of the source is. You could take a flashlight and run forward with it, and the speed of light is still going to be the same as if you were holding that flashlight at rest. Regardless of the motion of the source or the observer, or any presumed medium. Through which it propagates. By contrast, the speed of sound, if I say the speed of sound is 340 meters per second, I mean relative to the air, right? And if the wind was blowing toward you, then the speed of sound, of course, would be increased. If it's blowing away from you, the speed of sound would be decreased relative to you. But Einstein's second postulate says that the speed of light is one number, 3 times 10 to the 8th meters per second, regardless of the motion of the source, regardless of the motion of the observer, regardless of the motion of any medium that you might suppose that the light propagates through. It's just plain 3 times 10 to the 8th meters per second. Now I want to come back and tell you a little bit more about what these postulates mean. Yes?
When they shine a beam of light through cesium vapor, it's going 300 times faster.
That's not in vacuum, right? So is speed of light in vacuum? Of course, in going through glass or water or something like that, the speed of light is decreased. But that's basically because when the light goes through that water, it's bouncing all over hell to get through. So it actually went through went on a much longer trajectory than it seemed to have. So there's a sense in which, even in a medium, the light was actually always traveling at the speed c. It's just that it had to go by a more circuitous route, and from the outside that was always quite slower. But let's avoid the complications there by just saying speed of light in vacuum. So you say, okay, what is he talking about the medium then? Well, actually, we now don't believe that light requires any medium to propagate, but in the time of Einstein, people said, what is light? It's some kind of a wave. What is waving? Well, I don't know. We can't see it, touch it, feel it, taste it, or anything like that. They just called it ether. It's whatever does the waving when light goes through. So I should say any assumed medium, one of the consequences of special relativity, as you'll see, is that we dispense with the notion of medium entirely. So if you believe there's a medium for the propagation of light, then I state the postulate as independent of the velocity of the medium. If you don't believe there was any medium there in the first place, then rub out the last sentence. It's not doing anything for you. I mean, the last phrase. But I don't mean speed of light in a material medium, because then it is reduced for other reasons having nothing to do with it. So, those are the two postulates. Now I want to come back and tell you a little bit about exactly what each one of them means. The first postulate was nothing new. You can find it very clearly stated in the works of Galileo from centuries ago. Einstein liked to tell the story of relativity in terms of these homely parables that he called Gedanken experiments, thought experiments. And they're sort of fun, so we tell the story that way today, although, of course, in some respects you're not supposed to take them literally. They're designed very skillfully, Einstein's Gedanken experiments, designed very skillfully to show you the logic of an argument. So he said, what does it mean to say that the laws of physics are the same in a moving reference frame as in one at rest? The example that he liked to use is suppose that you have a billiards table, you load it onto a car on a freight train, and that car is going at constant velocity down a nice smooth track, smooth straight track. So here's your billiard table. And what the first postulate says is that the progress of that game of billiards is going to be exactly the same in that moving train as it would have been if the train was at rest in the station. You don't have to correct for the fact that the car was moving, that the train car was moving. Indeed, if you pull all the curtains, you would have no way of knowing from watching the progress of that game whether the train was moving or not. Does this make sense? By contrast, by the way, you know immediately if the train is accelerating. This is only for reference frame moving at constant velocity. If that train accelerated, for example, it speeded up or slowed down, went around a corner, went over a bump, something like that, you would know about it immediately, because the balls would roll in weird curved arcs on the billiard table, and you yourself would feel a strange lurch to one side. Even if the windows were pulled, you would know, the curtains were pulled, you would know very well that that train was accelerating. And you would spill the coffee on your shoe. So there are plenty of ways that you would know the laws of physics are not the same in an accelerating reference frame as they are in one that's moving at constant velocity. But what the first postulate says is that if it's moving at constant velocity, you have absolutely no way of knowing from anything inside the train the fact that that train was moving at all, because the laws of physics are exactly the same in that uniformly moving reference frame. That's what the first postulate says. By the way, I say that it was nothing new. It was known well to Galileo centuries earlier. If Einstein added anything to the first postulate, it was the arrogant assumption that this was true not just for the laws of classical mechanics, but for the laws of any kind of physics that you might discover in the future. Einstein was kind of that way. He might say, well, laws X, Y, and Z happen to be the same. He said every damn law that ever comes up is going to be the same in the moving reference frame as it is in the one at rest. And therefore, you have absolutely no way of knowing that that train car was moving. Let me run for you an example. Maybe I should write this down. Train accelerated. Nobody is saying in the special theory of relativity that the laws of physics are the same in an accelerating reference frame. Of course not. That's obviously untrue. But if the train is moving at constant velocity, then the laws of physics are exactly the same by that sense. So by contrast, you know immediately the train accelerates. Here's an example, just to show you exactly what I mean by saying that the laws of physics are the same. I mean, kind of physically, you understand what it is. You can play ping pong on a moving train, and nothing would be affected by the fact that the train was moving. But let's do an example. Suppose that I had examined the following collision process. I've got a cart of mass 2 kilograms, and it's going along at 3 meters per second, your classic collision problem on the air track or something. And it hits another cart whose mass is 4, so that's a scene beforehand. And they collide together, of course, and let's say that they stick together. So I've got a combined cart that's now 6 kilograms, and I would like to know how fast is that going. How do we do it? Conservation of momentum, of course. The initial momentum was Pi equals 2 times 3 is 6 kilogram meters per second. None for this. That's got to be equal to the final momentum, which is 6 times v. 6 equals 6 times v, so that tells us that v is equal to 1 meter per second. I make the numbers very simple because I want this to be an utterly straightforward problem. Did I do something wrong? So, there's the collision process. Now suppose that we examine that same collision process from the perspective of an observer who's running along at 3 kilometers per second to the right. What does it look like? The 2 kilogram object is now, well, you tell me what its speed is in this system. 0, right? It's going along to the right at 3 meters per second, but so am I watching it. So from my point of view, it's not moving. What's the velocity of the 4 kilogram object in this frame? Minus 3. It's coming at me at 3 meters per second. So there's the scene before. And what's the scene afterwards? The composite lump here. What's its velocity in this reference frame? Think it out.
-2.
-2, isn't that right? Because You know, it's going along at 1 meter per second, but I'm going along at 3 meters per second, so from my point of view, it's sliding back at 2 meters per second. How did I do these, by the way? What's the arithmetic? Maybe we should write this up here. The rule that I obviously used, you actually used, to get those, you subtracted 3 from each of these velocities, isn't that right? You took 3 minus 3 and got 0. You took 0 minus 3 and got minus 3. You took 1 minus 3 and you got minus 2. So you just subtract off the relative velocity. I'll write the formula down in a moment. Now, suppose that we asked the question, was momentum conserved in this reference frame? Well, let's check it out. The initial momentum in this reference frame was nothing for this, 4 times minus 3 for this, was minus 12 kilogram meters per second. That was the momentum before the collision. T final, 6 times minus 2 equals minus 12. Yes, momentum was conserved in that reference frame too, automatically. If it was conserved in the original frame, then it's automatically conserved in any frame that's moving at a constant velocity with respect to that, wasn't it? It wasn't an accident of the fact that this was going at 3 meters per second, of course. No matter what the constant velocity had been, you would find that momentum was automatically also conserved in that reference frame. That's what the first postulate tells you, that the same laws of physics apply in a moving reference frame as do in a frame at rest. In this instance, the law of physics in question was the law of conservation of momentum. If it was true in the original frame, then it's true in the other reference frame also. Notice that the numbers, by the way, are completely different. Nobody says that the momentum is the same in this frame as it is in this frame. Here the momentum was 6, here the momentum was minus 12. Numbers completely different. All we're saying is that the law of physics is the same in the moving reference frame as it is in the one at rest. Right? Law of physics being conservation of momentum, same after as before. That holds in both reference frames, even though the numbers themselves are quite different in the two. So, as I say, the first postulate was nothing new, well known to Galileo hundreds of years earlier. And probably just not something that most physicists thought was terribly interesting before Einstein came along and made it the foundation of the special theory of relativity. The radical postulate, the thing that changed everything, was the second postulate, the postulate of the universal speed of light. Indeed, on its face, the universal speed of light is absurd. Let me show you why. I often think that if I had been around in 1905, I would have read about the first page and a half of Einstein's paper and said, how on earth did this junk get published? It's obvious nonsense for the following reason. The second postulate is absurd. Because of the following kind of obvious argument. Suppose that I'm, again, on this train. And the train's going along at, let's say, 60 miles per hour. And of course, smooth, straight track going at constant velocity. But I'm feeling hungry, so I head forward for the dining car, which is up there close to the engine. Here's me. And I go at 4 miles per hour along the aisle. That's pretty good walking speed up the aisle. I ask you the question, how fast am I going relative to the ground? By the way, how many of you have studied special relativity before? Those of you who have, forget everything you knew, okay? It's going to confuse the issue if you're trying to tangle in future information that you know about relativity in with the argument here. So I'm telling this story as though you knew no relativity existed. So, question, how fast am I going relative to the ground? Answer? Somebody said it. 64 miles per hour. In fact, I'll prove it. Because let's say that we let this process keep going for 1 hour. How far has the train gone down the track? 60 miles. How far have I gone along the aisle of the train? 4 miles. Long train. How far have I gone relative to the ground then? Well, the train went 60 miles and I went 4 miles in addition to that. So I've gone 64 miles. How long did it take to do it? 1 hour by assumption. So I'm going 64 miles an hour. Simple as that. Hard to argue with. I'm going at 64 miles per hour. But now, suppose that well, let me write down the formula now that we were actually using. The velocity of me relative to the ground, A with respect to C. Velocity of A with respect to C, that's me relative to ground, is equal to the velocity of A with respect to B, that's me with respect to the train, at 4 miles an hour, plus the velocity of B with respect to C, the train relative to the ground, that's the 60 miles an hour. A equals B, me, B equals train, C equals ground, and my notation here means velocity of me relative to ground. Got the picture? That's the formula that I actually used there to get that one. That's actually the same formula that I used over here. Velocity of A with respect to C is velocity of A with respect to B plus the velocity of B with respect to C, and there doesn't seem to be anything but common sense built into that formula. It's not some formula, big formula of physics that you study for weeks in a freshman physics course, because it's just obvious. But the problem is that it's incompatible with Einstein's special second postulate, the universal speed of light. Because suppose now that instead of me walking down the aisle at 4 miles an hour, I'm going to shine a flashlight down the aisle and run exactly the same argument. So here I am, train, still going at 60 miles an hour. But now I'm shining this flashlight down the aisle, and when I switch it on, the beam takes off down in the forward direction. How fast is it going? Well, how fast is the wavefront propagating there? Presumably the speed c, the speed of light relative to the flashlight on the train. And according to the formula over there then, the speed of the light relative to ground is c plus, that's what was the 4 miles an hour before, plus 60 miles per hour. Of course, c is a huge number, so c plus 60, I'm never going to notice the 60 miles an hour in there. But in principle, that light beam is going at c plus 60 miles an hour relative to the ground, right? Exactly the same argument as before. But that's exactly what Einstein's second postulate says is not the case. Einstein claims that the velocity of light is c relative to the train, relative to the flashlight, relative to the guy standing on the ground, all of them. Not c plus 60, just plain old c. As I say, if I were reading Einstein's paper, when I got to the second postulate, started thinking about exactly what that means, I would have bailed out right there. This theory is nonsense and worthy of publication. Of course, Einstein was no dummy. He was very aware of this problem. How did he resolve the paradox? Einstein said that this formula here, the way that we've always added velocities, is just incorrect. Einstein's formula reads as follows. V, A with respect to C, the velocity of A with respect to C, is the velocity of A with respect to B plus the velocity of B with respect to C. That's the old obvious formula. But then he said you should divide that by 1 plus VAB, VBC, the product of those two, divided by the speed of light squared. This is what we now call Einstein's velocity addition law. And it replaces what, by contrast, we will now call Galileo's velocity addition law. The old common sense rule. It's got the same numerator, but then there's a correction factor that Einstein threw in the denominator. I have several things on my agenda now. First of all, I've got to convince you that this resolves the paradox, that now velocity addition is consistent with Einstein's first postulate. Secondly, I've got to explain to you why nobody ever noticed this before Einstein, if it's really true. And thirdly, I've got to account for the fact that this law, which I tried to prove a moment ago, and it seems like nothing but common sense, how could it possibly be wrong? So, there's the agenda. First item, how does Einstein's velocity addition rule resolve the paradox and salvage the second postulate? A very cute argument here. Let's do exactly what I was doing before. I shine a flashlight down the aisle of a train, and I would like to calculate what is the velocity, using Einstein's law now, what is the velocity of that beam of light relative to the ground? The light relative to ground is equal to velocity of the light relative to the train. That is c. In fact, according to Einstein, it's always c relative to anybody. Plus the velocity of the train relative to the ground, let's just call that v sub t. And now I'm supposed to divide it by 1 plus the product of those two velocities, c times the velocity of the train, divided by c squared. What does that do for me? Well, I see one of the factors of c here is going to cancel. and I think to straighten out the algebra, I'm going to multiply top and bottom by c. So I've got c times c plus vt in the numerator, and c times 1 plus vt over c in the denominator. You're following this for once. I want you to follow every detail of the algebra because it's beautiful and it's very clean. I'm going to multiply top and bottom by c. In the top, I've got c times c plus vt. In the denominator, if I multiply this in, I get c for the first term, plus in the second term, it cancels the c in the denominator, vt. Aha! You see what happens? The c plus vt here exactly cancels the c plus vt over there, and I get c. So, if the velocity of the light signal is c relative to the train, then automatically, using Einstein's velocity addition law, it will also be c relative to the ground, which is exactly what the second postulate claimed it was supposed to be. So it's magic built into this formula that if you're going at velocity c relative to one thing, you're necessarily going at velocity c relative to anything else, which is exactly what the second postulate says, at least in the case of light. Well, if this formula is true, and not the old Galilean one, how come nobody ever noticed this long before Einstein? Why do we notice it every time we get on the train and walk down the aisle? What's the answer to that? You know, the kind of an obvious answer. How come nobody ever noticed this correction factor down there if Einstein's really right? Yeah.
Since there's a c in the denominator there, you're basically just dividing by 1 unless the speed is always comparable to that.
Okay, I understood from the last part what you were getting at. Let's go back to the general case here. Ordinarily, VAB and VC are very much smaller than c. That makes sense? So when I'm dividing by c squared in the denominator, if I got
Like 1 plus 0.
4 miles, exactly. This term here is going to be 0.00000, you know, a 1 way down there in many decimal places. So it's not really going to be much of a correction at all, unless, exactly as you say, unless one or both of those velocities is comparable to the speed of light. Then that correction factor can become significant. But if you're really talking about 60-mile-an-hour trains and 4-mile-an-hour people, you're never in a million years going to notice that correction because it's a tiny, tiny little correction. But if you're talking about light moving around or rocket ships or something going comparable to the speed of light, then it really does show up. Then it becomes noticeable. So, answer? The correction. See, if I rub this out, the one is doing nothing. I'm just back to Galileo's formula. So the correction factor, VAB VBC over c squared, is ordinarily tiny. Because c is so huge. And it's only when one or both of the velocities are comparable to the speed of light that you're ever going to notice that correction term.
I probably shouldn't say this, but there's a bit of a problem here, because you've just introduced the addition law.
Yeah?
You didn't use in the first example.
Ah! How about that?
So I think in a couple of lectures we'll get back to that. But I do believe
We get back to it right now. How about that?
that's wonderful.
or at least, this is a beautiful point. When I did this little calculation down here about the air tracks, proving to you that the first postulate was right, at least in that instance, how did I add the velocities? I added them using Galileo's rule.
The wrong way.
Now we know that Galileo's rule is wrong. Should have used this one. That's going to fuck up that whole argument. Well, how about that? You know what the resolution to that is? That the complete resolution will come next week sometime. But how does that get doctored up? Well, Einstein changed the formula for momentum. He changed the formula for momentum, so it's not just mass times velocity, but actually, I'll get a little ahead of the game, mass times velocity over the square root of 1 minus v squared over c squared. He doctored out the formula for momentum in such a way that it just picks up the pieces that came from using a different formula for adding the velocities. So the argument that I gave there was a purely classical argument designed to show you how Galileo might have thought that the principle of relativity was true. When Einstein monkeys around with a rule for adding velocities, he's actually inadvertently thrown out the window the very argument that he was basing the first postulate on. But he had to come back and fix that by modifying the formula for momentum itself until he gets a formula. In fact, I suspect that he was motivated in his formula, in devising this formula precisely to make this happen, although I'm not dead sure of that. It's not entirely clear how he got the formula for momentum.
I actually got it in the second paper.
In the second paper?
Yeah, I think the first paper didn't have it.
Yeah.
Because
Maybe he hadn't even figured it out completely.
yeah, I think when he published the first one. And the other really remarkable thing is that when you do the same collision type argument and correct it, because this part is really right, that you just give it the velocity,
Right.
you get E equals mc squared.
Right.
And that's in
So
the second paper.
he had to, he modified not only the momentum, but also the formula for energy. And that's why E equals mc squared. But this is an
No, that's getting
argument
ahead.
for a head. But I'm glad you raised that because actually on the board for today, as far as today's lecture is concerned, there was a glaring contradiction there. I used the Galileo rule to justify the first postulate, and then threw away Galileo's rule in the second postulate. So there was an absolute inconsistency there. Glad you pointed to that. Did you have a question? No. Let's see, where was I? Oh, that's why we haven't noticed, wouldn't have noticed Einstein's velocity addition law in everyday life, because the velocity is just so small that the correction term is minuscule. But by the way, this might disappoint you, but Einstein's velocity addition rule also has built into it an algebraic fact, a weird algebraic fact, not entirely easy to prove actually, but the fact is that you can't get yourself going faster than the speed of light by running down the aisle of a train at high speed and having that train also be going at high speed. This has the property that if the two velocities are less than the speed of light, VAB is less than c and VBC is less than c, then VAC is also less than c. I don't know if you ever wondered about this, but everybody's learned that you can't go faster than the speed of light. That's a speed limit. Well, why can't you go faster than the speed of light? Simply by running down the aisle of a train that itself is going 3/4 the speed of light, and run down the aisle at 3/4 the speed of light. It sounds like you ought to be going then 1.5 times the speed of light. Yeah.
I was just saying, I was doing the math in my head, but even if you were going the speed of light on something that's going the speed of light, you're still only going the speed of light.
Right. Absolutely. That, if you like, is a special instance of this one where VT itself is c. Good point. But let's try it. It's kind of fun, actually. Suppose VAB is equal to 3/4 c and VBC is equal to 3/4 c. You'd think you could do it with a half c and a half c, and should add up to 1 c. But let's do it even more extreme. 3/4 c, more than enough. And down the aisle of a train that's going at 3/4 c, more than enough. This should surely get you going faster than the speed of light relative to the ground. Nope, I'm sorry. Let's stick it in. See what we get. VAC is equal to VAB, that was 3/4 c, plus BBC, that's 3/4 C, divided by 1 plus 3/4 C times 3/4 C divided by C squared. The C's cancel. In the numerator, 3/4 plus 3/4, 3/2 C. In the denominator, 1 plus 9/16, huh? Well, 1 plus 9/16 would be 25/16. 16 plus 9, 25/16. So the answer is 16 over 25 times 3 over 2 times C. 2 goes into 16 8 times. 8 threes are 24. Damn. 24 over 25. It's getting up there, but it's not quite C. And try any numbers you want, 0.999C and 0.999C. Stuff them into this formula, and you'll find you're getting creeping up very close to the speed of light, but you never quite make it. So you can't get going faster than the speed of light by loading yourself into a high-speed train and running fast down the aisle. C is the speed limit. Even if you use light itself, then it's still only going at the speed C relative to the ground. Now I want to come back and mention two subtleties. The first postulate says that the laws of physics, the way I stated it, the laws of physics are the same in any uniformly moving reference frame as they are in a reference frame at rest. You pull the curtains, you can't tell whether that train is moving or not. Well, in that case, how the hell would you ever know what a rest frame is in the first place? Any reference frame that we're on the surface of the Earth. But the Earth, you know, is rotating around its axis, it's revolving around the sun. The sun is moving through the galaxy, and for all I know, the galaxy is moving at high speed through the cosmos. We're certainly not a rest frame. How do we ever identify a rest frame in the first place? And if we don't know what's a rest frame, how do we know what's uniformly moving with respect to a rest frame? The whole first postulate said laws of physics are the same, you know, in a frame moving at constant velocity as they are in one at rest. If you don't know what one at rest is, and you have no way of knowing what uniform velocity relative to that is, what's the first postulate telling us? This is actually a piece of circular logic that we have to break out of. Since you can't find a rest frame in the first place, it's an embarrassing consequence of the first postulate that you can't identify a rest frame. How do we get around that? In the old books, they used to say a rest frame is one that's attached to the fixed stars. But we now know that the stars are anything but fixed. There's no such thing as fixed stars out there. Actually, we use now the first law, Newton's first law, as the way of determining whether you're in a legal reference frame. I define an inertial reference frame that's a reference frame in which the first law, Newton's first law, holds. How do I test that? Get a bunch of rocks and throw them around. And if they go in straight lines at constant speed relative to me, then I conclude, I'm in an inertial reference frame. The first postulate should really be stated then that the laws of physics are the same in all inertial reference frames. Then I've never made reference to a frame at rest, and I'm not into that circular logic of how do you find a frame that's at rest. This logically best starting point is define an inertial reference frame. That's one in which objects that are unaffected by forces moving constant velocities. Once you identify an inertial reference frame, any reference frame moving at constant velocity relative to that is likewise an inertial frame, and all such frames are legal for doing business of physics. That's what the first postulate says. I have your exams, which were wonderful, by the way. The median was 85. They ranged from 28 to 100.